Hey guys, welcome to week number 3 of the Ace Your IB Math Exams in 10 Weeks series. We're going through every possible topic, every possible type of question that might show up in your upcoming IB Math exam down the line in May 2026 this year, where each week we tackle 5 questions from all 5 different topics of the IB Math curriculum: number and algebra, functions, trig, probability and statistics, and lastly calculus. All of these questions, they are challenging, they're all fun to do, they're going to give you a sense of what the IB Math exam will look like. They're novel, they're new, you're not going to find them anywhere, so it's a very good resource to better prepare yourself for the upcoming IB Math exam. If you missed one of these weeks, one of these lists, you can find them in the description of this video, and do share them. Share the link for the YouTube videos and also the PDFs with your colleagues so you guys can study together. So without further ado, let's start week number 3 of the Ace Your IB Math exams in 10 weeks. An induction proof exercise, but this is an induction proof that involves divisibility, which is not the hardest type of induction proof. Now, if you want to dive deep into induction proofs, there are many more videos on induction proofs in this channel. Now let's tackle exercise number 1. We need to prove by induction that 3 to the 2n plus 4 minus 2 to the 2n is divisible by 5 for all positive integers. Now we're going to go through the 5-step process in solving any induction proof exercise. And step number 1 is to write the propositional function, which is what you're trying to prove. So number 1, P of n. Our P of n is 3 to the 2n plus 4 minus 2 to the 2n is, you're pretty much just copying the exercise, is divisible by 5 for all positive integers. Now step number 2, that's the base case, which, given that we're talking about positive integers, it starts at 1, therefore we're going to replace n by 1 to prove the base case. So we have 3 to the 2 times 1 plus 4 minus 2 to the 2 times 1, which is 3 to the 6th minus 4, so 729 minus 4, 725. Which is a multiple of 5 or divisible by 5. It can be written as 5 times 145. And it's important to restate which is divisible by 5. Therefore, the base case holds. Don't forget to write this. Now let's jump to step number 3, which is the inductive hypothesis, also known as P of k. We are going to assume that 3 to the 2k plus 4 minus 2 to the 2k, so replacing our n's by k, is divisible, or it's a multiple of 5, meaning that it can be written as 5 times some integer. So we're going to define capital A as a positive integer. And it's also very important to say that we're assuming that this is true for some positive integer k. Now on to the hardest part, which is the inductive step, P of k plus 1. When we have induction proofs with divisibility, the way to address P of k plus 1 is to rewrite our P of k, but replacing k by k plus 1 and substituting this P of k over here. And hopefully, if you do everything right, get some multiple of 5. You're going to be able to factor out a 5. Do notice that you can do that because you're assuming that this is true. Let's first rewrite this in a more friendly way. We have 3 to the 2k plus 6 minus 2 to the 2k plus 2, which can be written as 3 to the 2k times 3 to the 6th minus 2 to the 2k times 2 squared. Don't forget your exponent rules. And we can replace 2 to the 2k using this equation by 3 to the 2k plus 4 minus 5a, which means that we're going to have 3 to the 2k, 3 to the 6th, minus 3 to the 2k plus 4 minus 5a, which is the green part on top, times 2 squared. Now let's continue simplifying this. We have 729, which is 3 to the 6th, times 3 to the 2k, minus 4 times 3 to the 2k times 3 to the 4th, which is this product here, plus 4 due to these two negative signs, times 5a. So 729 over here, 324 over here, and 20a. Factoring out 3 to the 2k, we get 729 minus 324. So 405 plus 20a, and there you go. We can indeed factor out a 5. we have 81, 3 to the 2k, plus 4a, which is divisible by 5. Now the last part, which is the most boring part, is to vomit the conclusion. It's just one sentence that you have to write every time you tackle an induction proof. It's got to be there. So number 5, the conclusion. Given that p of 1 is true and p of k plus 1 is true whenever p of k is true for some positive integer k, then by the principle of mathematical induction, you can write PMI here. It makes it shorter. P of n is true for all positive integer n's. And there you go. In exercise number 2, we have a quadratic function. So over here, we're going to talk about quadratic functions, vertex form, standard form, how to find a vertex, inverse functions, and also function transformation, which is a topic that students usually freak out about. Now let's get through all that together. Consider the quadratic function x squared minus 2x minus h, which was defined for x less than or equal to 1. What we have here is a quadratic given in standard form. We're going to convert, and that's exercise A, to vertex form, which means that you should either complete the square or find the vertex using the negative b over 2a formula. Given that completing the square is a technique which not everybody is comfortable with, however, I do suggest that if you don't know how to do that, you do learn it, given that it's super fast. It's much faster than using negative b over 2a, for example. I am going to find the vertex using negative b over 2a, so we're going to go through that process. So how do we find the x-coordinates of the vertex, which in this case is calling h? H is negative b over 2a, and by a and b, I mean the coefficients of this quadratic. A is equal to 1, b is negative 2, and c negative 8. So we have negative 2, positive 2, over 2 times 1, so h is equal to 1. Now, just to reinforce, this is the quadratic given in standard form, and this is the same quadratic given in vertex form. Whenever you want to find the inverse of a quadratic, you gotta have it written in vertex form, and that's what we're gonna do for question B. Now, back to question A. We did find the x-coordinate of the vertex. How do we find the y-coordinates of that vertex, which, by the way, we're calling k here. Now, k is the function evaluated at that x value that we got, which means 1. And f of 1 is 1 squared minus 2 times 1 minus 8, so negative 9. Therefore, h is 1 and k is negative 9. Alright, so why is that when we want to find the inverse of a quadratic, we need to use the vertex form? Well, if you start out with the vertex form of this quadratic, and knowing that by finding the inverse you need to replace the y by x and the x's by y, in this case there's only one x that shows up, it becomes easy to isolate y now. So we have x plus 9 equals y minus 1 squared, which means that y minus 1 is positive and negative x plus 9, so y is 1 plus and minus the root of x plus 9. Now, only one of these two options, the positive and the negative, they're correct. And a nice hack to check which one of these two is the correct one is to use one point from the original function. So if you take, for example, any point which is less than or equal to 1, given that we're obeying to the domain of this function, let's say when x is equal to 0. We know that when x is equal to 0, y is negative 8. If the function goes through this point, the inverse will go through the point negative 8, 0, given that the inverse will flip the x and the y coordinates. Now, for us to have a negative 8 and a 0 here, the only way is for this sign to be negative. It wouldn't work if it was positive. We would get 0 equals 2. So therefore, our inverse is 1 minus the root of x plus 9. So 2 down, 1 more to go. Now consider a second function g of x such that we have a few transformations done to f, which gives us g of x. And let me color code all of them here. We have this negative 2, we have this negative 3, and we have this negative 8. What you can do as well is refer to this transformation as a separate one, which is easier to list. So in order in which they're applied, we have a horizontal shift 2 units to the right, we have a vertical stretch by a scale factor of 3. We also have a reflection about the x-axis. And we have, lastly, for this -8, a vertical shift 8 units down. And these are all the transformations in the correct order. Now, to find the intersections between f and g, we could, or should actually, find our g of x first. So -3 times f of x minus 2, which means that we take our f of x and substitute x minus 2 over here. Do remember that h is 1 and k is -9. So what we're going to have is x minus 3, which is x minus 2 minus 2, squared minus 9, and all that minus 8, which gives us -3. X squared plus 18x minus 8. So where's this equal to this? Well, we need to find where x squared minus 2x minus 8 is equal to -3x squared plus 18x minus 8, which means 4x squared minus 20x equals 0. If you divide everything by 4, you get this, and factoring out an x, you get either x equals 0 or x equals 5. Now, given that we know that x has to be less than or equal to 1, there's only actually one solution, which is this one, x equals 0. All right, so on to exercise number 3. This is going to be a longer one just because we have to go through the row echelon reduction, which is kind of a long process. And also, we're going to take these planes, these 3 equations, and we're going to assess all possible cases, everything that might happen whenever we change this constant m. So let's start. Consider the system below, where each one of these equations, they represent a plane. We're going to take this system, and in order to do a row echelon elimination, we need to come up with a triangle of zeros for these 3 coefficients here, which will turn out to be this. Now, it is much faster if you go through that process only writing the coefficients for these variables and whatever shows up on the right hand side of these equations, which means we're gonna have 1, 2, -1 and 0 for the first line, 1, -m, -3 and 0, and 1, 3, m and m here as well. Do notice whether in your first line or first equation the first coefficient is 1. If it's not, make it into a 1, which might involve dividing or multiplying by something or by swapping with one of these other equations. In this case, we're fine. Now, the second thing that you need to think of is what row operation would make me from this 1 on the top equation to eliminate this 1 from the equation below it. And the operation is, we're just going to take row 1 and subtract row 2 from it and store our value into R2 or row 2. So we're going to do row 1 minus row 2 and store that in our row 2. We copy the first row and we do 1 minus 1, which is equal to 0, and then we store it over here. We do 2 minus -m, which is 2 plus m, and we store it over here. 1 minus -3, so positive 2 over here, and then 0 minus 0. And that's it for equation number 2. Now for 3, we coincidentally are going to do the same thing. Given that we want to eliminate this 1 over here, we're going to do R1 minus R3 and store that into our R3. So we're going to have 1 minus 1, 2 minus 3, -1 minus m, and then 0 minus m, which is of course minus m, or -m. Now what we want to do is to do the same thing, but now eliminating this coefficient right here, which is the only one that didn't get converted to a 0. Remember that you want a triangle of zeros over here. Now, what row operations should we do in order to accomplish that? We can take our row 3, multiply it by 2 plus m, and add it to row 2, and then store our answer in row 3. What does it mean to multiply row 3 by 2 plus m? Well, we're gonna get over here 0 minus 2 plus m as the second coefficient, and then -1 minus m times 2 plus m, and for the last one, -m times 2 plus m. And when we add row 2 to it, what we're gonna get is 0, 0, which was the purpose in the first place to eliminate this guy, negative 1 minus m times 2 plus m plus 2, which if you want to calculate separately gives you negative m squared minus 3m, and then for the last coefficient, negative m times 2 plus m. Therefore, we get for row number 3, 0, 0, negative m squared minus 3m, and then negative m 2 plus m. You can also write this as negative m plus 3. And if you want to multiply this whole equation by negative 1 and store it in itself, and do remember that each line, each row represents an equation, you can, and that becomes m plus 3 over here, and then positive m 2 plus m over here. Therefore, we get the following system, which is exactly what we needed to prove. Now, let's jump to the next question. We're pretty much assessing what m needs to be in order to have no solution, infinitely many solutions, or one unique solution. So pretty much every possible case. So this exercise is very complete. It gives you a broad overview of all cases. So what does it mean to have no solution? That means that for the last equation, you get an equation that makes absolutely no sense. It's false, meaning, and emphasizing this last equation, that you get 0 over here and not 0 over here, which means that you get something like 0 equals 12, which obviously is not true. So how can that be the case in this scenario here? For us to get a 0, we either have m equals 0 or m equals negative 3. However, if our m is equal to 0, then this will be 0 as well. So this is not valid. This does not produce a no solution answer. Let's try it with m equals negative 3. If m is equal to negative 3, we have negative 3 times negative 3 plus 3, which is 0. Z equals negative 3 times negative 1, which means that we get 0 equals 3, which, of course, it is false. What does it mean? It means that we have no solution if m is equal to negative 3. Now let's consider the other scenario, which is to have infinitely many solutions. What does that mean in terms of the last equation? It means that we get 0 equals 0, so we pretty much throw the equation away. And in order to get 0 in both sides, we will need m to be 0. In this case, we get 0 equals 0 as the last equation. And if that's the case, and by substituting every m by 0, we get x plus 2y minus z equals 0, and 2y plus 2z equals 0 as well. Now, we are going to use the parameter t to represent z, where t is a real number, which means that 2y plus 2t is equal to 0, now taking this second equation right here, which means that y is negative t. And we also know by working with this first equation that x plus 2 times y, which is negative t, minus z, which is t, this is also equal to 0. Therefore, x equals 3t. Now, the solution is a line. With parametric equations, x equals 3t, y equals negative t, and z equals t, where t is a real number. The direction vector of this line, by the way, is 3, negative 1, and 1. And we can see also that it crosses the origin. Now, in order for us to have a unique solution, m cannot be equal to negative 3, and it cannot be equal to 0 as well, which means that if you focus on this last equation right here, you have your z as m2 plus m plus 3. Now we can cancel out the m's. It is not equal to 0, so we have m plus 2 over m plus 3, which means if you replace that here into the second equation, we have 2 plus my plus 2 times m plus 2 over m plus 3 equals 0, which means that y is equal to negative 2 over m plus 3. And if you replace both y and z over here into the first equation, you get x plus 2 times negative 2 over m plus 3, which is y, minus z, and this is equal to 0. Therefore, you get x after simplifying as m plus 6 over m plus 3. All right, so we're almost done. Now question C. Consider now that m is equal to 1. Therefore, we do have a unique solution. Given that the unique solution is the point m plus 6 over m plus 3, negative 2 over m plus 3, and m plus 2 over m plus 3, if m is equal to 1, we have 7 over 4, negative half, and then 3 over 4 as the point of intersection between all three planes. Now we need to find the Cartesian equation of the line which crosses the intersection, meaning that point, perpendicularly to this plane right here. So you have the plane and the line crosses it perpendicularly, meaning that the direction vector of this line is the same as the normal vector of this plane, meaning 1, 3, 1. Given that we're talking about the Cartesian equation, we're going to have 1, 3, 1 as the direction vector, x minus the x-coordinate of the point, y minus the y-coordinate of the point, and z minus the z-coordinate of that same point. And there you go. All right, so in exercise number 4, we have a little game being played. And let's picture these 4 people sitting down, forming a circle. So we have Adam, Bruno, Carlos, and Dimitri. And they are tossing a biased coin, one where the probability of landing heads is 1 over 4, which means, of course, that the probability of landing tails is 3 over 4. We know that the game proceeds in alphabetical order, so Adam goes first, and they take turns like this. Whenever head is obtained, the person is declared the winner and the game ends. So we're going to start with Adam and then go clockwise according to this diagram, of course. So what's the probability that Dimitri wins in his second toss? Well, if the person is declared the winner whenever this person obtains a heads, that means that before Dimitri has his second chance at tossing the coin, nobody should win, which means that Adam is going to toss it and he's not going to win, and Bruno is going to toss it and he's not going to win. This not right here is representing not winning. And then we have not Carlos, not Dimitri. Well, not for the first time, not on the first toss, only on the second one. So we need to go around once more. Then again, not Adam, not Bruno, not Carlos. And then Dimitri wins, which means that we have tails and then tails again and then tails again, all the way up to Dimitri's second toss, in which he does toss a heads, so he wins, which means probability is equal to 1 over 4. So in this case, the combined probability is 3 over 4 to the power of 7 times 1 over 4, which is approximately 0.0334. Now on to question B. What's the probability that Dimitri gets a third toss? That means that on the first round, nobody can win. On the second one, same thing. And on the third one, he gets the chance to actually toss it the third time. But do notice that it's not being mentioned here whether Dimitri wins that third toss or not. So the coin just needs to get to him on the third round, which means that on the third round, we have A naught, B naught, and C naught combined. So this is the first round, this is the second round, and this is the third round. So the probability here is 3 over 4 to the power of 11, which is approximately 0.042. And again, do notice that it's not being stated whether Dimitri wins or not. Now for C, we have a different scenario. We want the probability that Dimitri gets exactly 3 tosses, which means that we need to take into account the cases where he wins and that he does not win. For him to win with 3 tosses, we just need to continue this and state that he won on the third toss. However, we do have different situations. This is only one of them. In this case, Dimitri wins on the third toss. And what we have over here is 3 over 4 to the power of 11 times 1 over 4, which represents him winning. This is approximately 0.0106. And what are the other cases? Well, he might miss and Adam win on the fourth, or he might miss and Bruno win on the fourth, or he might miss and Carlos win on the fourth toss, which can be represented like this, which means that the probabilities are 3 over 4 to the power of 12 times 1 over 4, 3 over 4 to the power of 13 times 1 over 4, and lastly 3 over 4 to the power of 14 times 1 over 4. And if you add all of them, you get 3 over 4 to the power of 11 times 175 over 256, which is approximately 0.0289. And that's it. Kind of a long exercise. And for this last exercise, exercise number 5, we're going to tackle a related rates problem, one that involves a square base pyramid. Let's get to it. This is the last one. So we have a tank full of water that has the shape of a square base pyramid. This tank's perpendicular height is 12 meters, which means that from here to here, this height is 12, and this square base is 4 by 4. And we are going to use the letter H to specify the height at any given moment, the height of the water. So the water level is H. Now we know that the volume of a right pyramid is 1/3 of the area of the base times the height. This is a formula that's in your formula booklet. And the base is a square, so it's 1/3 times the area of that square times the height. And this means that at any moment, this volume is 1/3 times the area of this square. And we can call the side of this square x, so x squared times h. Now we can see that in the formula that it was given, we don't have any x, we just have volume as a function of the height, which means that we have to rewrite x as a function of h. And we can do that by using similar triangles. If you take this right triangle, you'll be able to see that this length, which is, by the way, half of this, it's equal to 2. It is proportional to this one, which is x over 2. The same way that 12, which is this total height, is proportional to this h. So this proportion remains. Therefore, we're using the concept of similar triangles, which form a proportion, which follow a proportion. So 2 over x over 2 is equal to 12 over h. If you cross multiply, you get 2h equals 12x over 2, which means that x is h over 3. And if you replace your x value here, what you get is 1 over 3 h over 3 squared times h, which is h cubed over 27. Now there's a leak, and its rate is 0.2 meters cubed per minute. And if the water is leaking, that means that the rate is negative. Therefore, dv dt, which is the rate of change of volume with respect to time, is negative 0.2 meters cubed per minute. And we need to find the rate of change of h when h is equal to 5, specifically at that instant, at that moment, or for that height. Now, given that v is h cubed over 27, we know that differentiating everything with respect to time will give us the rates that we're looking for. So the derivative of v with respect to time, dv dt, equals 1 over 27, which is just a constant that's multiplying h cubed, times the derivative of h to the third power, which is 3h squared. Don't forget about the dh dt that shows up over here. Now we know that the leak is negative 0.2. We know that h is 5, which means that this is 25. We can simplify 27 with 3. Now cross multiplying, we get dh dt equal to negative 0.2 times 9 over 25, which is negative 0.072 meters per minute. Now onto the hardest one. We need to find the rate of change of the square area on top when the when the volume is 8 meters cubed. Now if you start with the formula for the volume with respect to the area of the base, you can already, from this equation, and remember that this is the area of the base, differentiate this with respect to time. And by doing so, we can see whether we have all the information that we need, or if we need to find something else which is missing. So let's do just that. Differentiating this implicitly with respect to time, we have dv dt equals 1 over 3. And given that both area and height, they change with respect to time, you got to use the product rule here. None of these, they're constants. So we have the derivative of a times h plus the derivative of h times the area. Now, what are we trying to find? We're trying to find this quantity over here. We need, for that particular instance, when the volume is 8 meters cubed, we need the height, which we can find because we know that the volume is 1 over 27 times the height cubed. Therefore, h cubed is 8, which is the volume, times 27. So h is 2 times 3, which is 6 meters. We also need the area, and to find the area, we need to find x first. Now x is h over 3, which means that it's equal to 2 meters. Therefore, the square area is 4 meters squared. We also need dh dt, which we found before, but for a different instance. So we need to recalculate that. It's going to give us a different result. Given that v is 1 over 27 h cubed, dv dt equals, and again, we did this already, but we're now plugging in different numbers. The leak is 0.2. That's actually the same, but the height is 6. So we have negative 0.2 equals 1 over 27 times 3 times 36 dh dt. So dh dt is negative 0.05 meters per minute. And now, given that we know what dv dt is, this is negative 0.2, we have everything that we need. So we have our h here plus negative 0.05 times 4. So negative 0.6 equals 60 ADT minus 0.2. Therefore, dA dt is negative 1 over 15 meters squared per minute. So a very challenging related rates problem to wrap this up. And that's it. That was week number 3. I'll see you next week in week number 4 of the ACE or IB math exams in 10 weeks. If you missed one of those, check the links in the description of this video. You're going to find the PDFs there. You're going to find the other videos there. And do share that with your colleagues so you guys can study together. I'll see you next week.